So now we'll see topological sorting, and this is in directed acyclic graph. So this kind of sorting usually happens in a graph where it's a directed graph and there should not be any cycle. So we need to understand this because there are many problems in a lit code based on this problem. So let's understand this kind of sorting, and then in another problem we just borrow this code and then solve the problem. So if you see this example, this is a directed graph and there is no cycle. So for this one vertex there are 2 and 3 and the 4, and for the 2 vertex 2, 5 and 3. So topological sorting is called like u must come before v. So if you see that this is considered u, and then this u must come before v, so v2. So if you see here the 1 here, so if you the output will be, if you see here in this case 1 comes, and after that if you see the 2 and the 4, 2 and the 4, so this order doesn't matter, like the first 2 can come or 4 later, that's fine, that order can be different, but one thing we can make sure, this node comes before and then this other node. So if you see the 2 and the 5 3, 2 comes first and then 5 3, then 5 3 here. So this kind of sorting can be solved using the DFS or BFS, but let's use the DFS. We have done so many graph problems using DFS, and based on that try to solve this. So first of all we'll create the graph data structure. So based on this, if you see this, 1 is the key here in a map, and 2 3 4 it's a value, and for the 2 key and the 5 3 3 5, that's the value. So in this way we can create graph data structures. We see the code here also for the 1 2 3 4 and the 2 3 5 2 3 5. So we created the graph data structure, and we are calling here topological order, and we pass the graph, and if you see the result will be 1 4 2 5 3. So 1 4 2 5 3. So how will you do? So when we can start DFS from 1, and then we can go to the 2 3 4. So for 1, like we can see what are the neighbors. So there are neighbors 3 4 2 3 4. So when we come to the, let's say from 1 we visit neighbor 2, and from 2 we can see what are the other neighbors, so 5 and 3. Then let's say we can visit 3, and after that 3 there is nothing, then the 3 we can put that in a stack, and then after that come back here, and then we can go to the other neighbor of these 2, and we see the 5 here, and there is no other neighbors, then we can put this 5 in a stack 5, and then come back to the 1, we'll go to the 3 is already visited, so we'll not go to 3, go to the 4 and mark it visited and put that in a stack, because after that there is no other neighbors. So in this case all these neighbors of the 1 visited and put that in a stack, and at the end we can put 1 in a stack, and from the stack we can get item 1 by 1, and the order will be like this 1 4 2 5 3. So that's the topological sorting. So let's see the code here. Code is also very much similar to the other graph problem. So this is a topological graph order. I pass the graph, I create the stack. So when I go and visit this, and when I reach to the end, then I can put that item in a stack. So that's why there is a stack data structure here, and I need to know what are all the vertices. So for that I created a map, and in a map the key will be in all this value 1 2 5. So just I want to collect in all these vertices in a map, and the value will be a struct, empty struct. So that means there is nothing. So I do not want to use these values, just I want to use this so that I can store all the unique values. So if I come 2 twice, the 2 will be replaced with the 2. So just I want to get all these keys. So that's the vertices. So from the graph, I'm getting the key and then the value. So when I get the key 1, value will be 2 3 4. So for the vertices, I put that value like this key 1 and empty struct, because the value I do not care the value. So for this key I put that, and then the array, we also get the value as an array. So we want to get 1 by 1 item. So just I need a iteration here for array and get the item v. So it's a v in the vertices p, and I put the empty struct there. So in that way, I collected all the vertices. So now I can safely do the DFS, because now I have all the vertices. So I can start with any vertices there. So if I need to maintain a status. So for this status, I create the map, and in a map I'm going to put this key, any of this key, and the value will be visited or not visited, or 0 1. So not visited. So that's the int I can put here. So now we have all the vertices collected. So then we iterate through all the vertices and we'll get the item one by one, and we'll check that item. Let's say we get 1. So we'll check that 1 not visited. Of course, this 1 is not visited at the first time. So if it is not visited, then we can run the DFS, and in the DFS we can pass the graph, a stack, and a status, and this k. So that means we pass this 1 here. So come to, and this part I'll tell you later, but anyway, so when we get all the item in a stack, when we collect it, then we get the item one by one from the stack. So from the stack, from the top, I'm getting the item one by one and then putting in the result, and I can return the result. So the last portion is, you can see the DFS, how we run the DFS. So first of all, when you go to the 1, we mark it visited. So status, and this status is also map here. So in a v, so that one is the key here. So 1, and the value is also int. So in that case, I can put the visited. And for this one, I get the neighbors. So for graph v, for 1, I get the neighbors 2 3 4. So all this neighbor. So let's say we come to the neighbor 2. So we'll check in a status, neighbor 2 not visited. Yes, is the 2 is not visited. So again we'll call the DFS. So call the DFS again, we start from here, and the 2 will mark 2 visited. So for this 2, we mark it visited. And again for the 2, we'll get the neighbors. So we'll get the 3 and 5. So neighbor, and we'll check the 3 is visited. No, it's not visited. Then again we run the DFS on this 3. Again we come back here, and 3 we mark visited, and we'll try to get the neighbors of 3. So but there is no neighbors, so we'll come outside of the for loop, and in a stack we can put this 3. So we'll put in a stack, we'll put this 3 here in a stack. So 3 is done. Then we'll come back to 2, because for the 2 there were 2 neighbors 3, so 3 work is done. So we'll go for the 5. So here we'll check a status 5 not visited. Yes, it's not visited. Then we'll go for the DFS of the 5, and again we come to this function and make a status 5 visited. So this is visited, and then we'll try to get the neighbors of graph v, that is 5. There is no neighbors. Then come out of this loop, and we can put that in a stack. So we can put 5 in a stack. So that's 2 is there's 2 neighbors done. So the 2, for this 2 neighbors, one by one, all the DFS done. Then at the end there is a 2 remaining. So come out of the loop and then push back 2 itself. So 2 is in a stack now. Then from here we go to the 1. Then from 1 we go to the 3, but 3 is the 3 is for the 1, the 2 neighbor is done. There are 3 neighbors like 2 and 3 and 4. So 2 is done. So we'll go for other neighbor, but 3 is, since 3 is already visited, so it will not go here and come back here and push back. it will not push back, because it will come at 3 is already visited, so it will not go there, but still there is a one remaining neighbor 4. So it will go to the 4 and call the DFS, and again 4 will mark visited, and then for 4 we'll try to get all the neighbors. There is no neighbors, then come outside and push back this 4. So 4 we'll put that in a stack, and then come back to the 1. So all the neighbor of 1 work is done. So for the 1 we can come outside and we can put that 1 also in a stack. So in that way you put that in a stack. We come back here, and because here we pass that stack, so all the value collected in a stack, and from the stack we get the one item one by one out of that. And that's called the topological sorting. And we'll make use of this function in many functions or many problems in a lit code. Sometimes we'll also may have to modify this function a little bit, because sometimes there is a cycle. If there is a cycle, then in that case we need to return nothing in this case. So let's modify the code for that here. So I'm just going to copy this function, and I'm going to rename this topological order with cycle, or topological order when cycle. If cycle detected, then what we do in this case. So here on this function I'm just going to rename is a DFS2, and we call the DFS2, and in this place we'll call the DFS2. So for the cycle, in order to check for the cycle, we need 3 variables. That's we also did in other graph problems in the previous videos. So let me create one more variable here. It's a const in a stack is 1. Okay, topological order with cycle. So the rest of the code will be same, only the changes will be in the DFS2. So when we come, like let's say let's create one cycle in this case, like from the 2, okay, from 5, let's say from 5 again we can go to the 1. So for the 5, if you go to the 1, then I can add one more key here. So let me put that key in this place, like 5, and from the 5 we can go to the 1. So 1. So in this case we want to return empty list in this case. So I'm just going to comment this out and call the another function, topological order when cycle. Okay, so let's write the code for that DFS. So first time when we come to this 1, I can just say that it's not visited, but I can say that that's a stack. That's in it's a, let's we put that in a stack, yeah. In stack. In a stack, S capital. So we come to this place and we put that 1 in a stack. So that's good. And for 1 we'll get the neighbor. So for the 1 we'll get the 2 5 neighbors for the 2, and again when you go to the 2, and we'll get the neighbor 3 and 5. So for the 2 also we put that in a stack. So we'll check here, 2 also we put the stack, but when you go to the 5, that the neighbor is neighbor for this 2 is 5, and for the 5 and 3, and when we go to the 5, again neighbor for the 5 is 1. Like let's assume that there's a connected here. So if the 1 is connected, from the 5, then we'll see, okay, one is in a stack. So for this node, the neighbor 1 is in a stack. If 1 is in a stack, then we can return true. That means there's a cycle detected. So for that, let's return the boolean value, and I can check this condition here inside this. If a status neighbor is in a stack, then I can return true. That means there is a cycle detected. And in other case, if a status neighbor not visited and it is not visited, and this and the DFS2, like if there is a cycle, then also we can return true here. So this we can put the DFS2 cycle. So this is actually detecting the cycle. If there is a cycle, then it's not visited, and the cycle, then return true. Otherwise, at the end, we can return false. And then a stack post v, and here we can say status v is visited. So let's run this, and then again we'll see the flow. Come back and see the flow. So push back this example, we're calling this, and I'm assuming this time it should return empty list. So for that, we can check this condition topological order when we call the DFS2, and if it returns true, if there is a cycle, then we can return empty list. Otherwise, at the end, anyway, it's going to return the result. So let's save it, run it. 17, we need a comma here. Okay, see, that's the empty list here. But if I remove this, then still this function works for the normal topological order. If there is no cycle, then it's good. So we can use this one. So this is very useful function here. So let me call this. Okay, so this time also did I save? No, I have not saved. Okay, this time it's working as a normal, or topological order function. So mostly we'll use this function topological order when cycle in the problems. Whenever there is a cycle, then if we detect the cycle, then just return nothing. So there is no topological order in this case. So that's all the code about this. So that's all for now. Okay, thank you.